think it's you.
Let's see if it works. All right, thanks. Yeah, good. Thank you. Hello, everyone. It's a pleasure to be here. I'll try to keep you awake after I've got. Is that right? 10 minutes?
Oh,
no. Okay, don't start it. Don't start it. No, don't start it. It's okay. So the original, I don't know if you see all the agenda. The original talk I was supposed to give that Vukosi mentioned that we had talked about is this had to do with AI and research and stuff like that. And that's not what I'm going to talk about. Although it is very, very related, and it's actually related to the reason why I got into that kind of work in the first place, which is around this question that we've been hearing about a lot around sort of epistemic inequality, and the epistemic inequalities that can be embedded within AI models, particularly large language models. So I'll start with a little story about now it must be 2 years ago. I was sitting in a team meeting, and I'll tell you where I work in a second, but I was in a team meeting and someone came in and was like, wow, I was reading this report. It was amazing. It had this one stat and it was exactly what we were looking for. And then I went and I looked and I looked and then I found the reference, and then I tried to find it and I couldn't find it anywhere. And of course, you guys have all heard about this, right? This hallucinated references. It happens. I work at a place called IDRC, so it's International Development Research Center, and we fund research for development. So this is it's a threat to research integrity, right? This is a threat to our reputation. We're putting stuff on a website that has a fake reference on it. That, first of all, it just looks really bad, but it also, anyway, I think we all understand the potential implications that this has for the credibility of research. And we're all here because I think we believe in the credibility and the importance of research. So when I heard that, actually didn't take me long to go quickly find some other examples. Then I thought, okay, this is a real problem. Within our organization, we didn't know how we were going to deal with AI just yet. We didn't have any policy. And then I thought, being someone who has just enough technical skills to mess around with things, I thought, you know what? I bet I can build something that will detect whether or not there's a reference that's been hallucinated. And I didn't start with the idea of, okay, let's detect something that is AI generated. We can have a discussion about that, but I don't think that's possible, and it can always be gamed. But I thought, okay, actually a reference is something real. There's a ground truth. You can find it. So I thought, okay, let's see if we can build something, of course, using AI to detect AI. And I did. I built something. It's called Source Verify. This is what I was talking to Vukosi about. Anyone wants to talk to me about it, happy to talk about it. This is not what I want to talk about here. What happened after I got this finally working, and by the way, you can build a pilot of these kind of things in like the weekend, but then to really get it to work, man, that's a year worth of work. What I realized, though, as also kind of a researcher, is that this can be a really good research tool. And since we fund a whole lot of research and innovations across sub-Saharan Africa, and I live in Senegal, I thought, geez, I wonder if when we do research on, say, West Africa, if we get more hallucinated references back than if we're doing research, say, on the US or the UK. And so I thought, geez, let's ask that question, right? Because now I have a way to automate the finding if a reference is hallucinated or not. And so I picked those particular countries because they lined up very nicely. I don't know if you know OpenAlex. It's an open research database of academic and scholarly work. And if you look up and you do a search on United States, you get about 80 million academic pieces. If you do on Nigeria, you get 700,000. And you see Ghana, it's only 100,000. So orders of magnitude in difference, right? And of course, I'm coming into this without a great background understanding of large language models, although I'll get to scaling laws in a little bit. But from my perspective, everyone talked about bias in data. And my assumption was, well, that's going to be driving this. So let's check that out and see if it worked. And it did. So I ran it on 2 models. And what I did was I asked it, actually, there were 2 different types of prompts that I did. The most important thing is each prompt, I was asking them to return 5 references related to a specific subject, so health, education, it got more specific, and then in country X, right? So in the United States, second one is Nigeria, and the third one is Ghana. The blue is GPT-5, which at the time was the newest and the biggest. And GPT-5 Nano, which is small. We don't know the size of the parameters, right? But the difference is very clear. If you use GPT-5 Nano to do research in Ghana, I mean, it's catastrophically bad, right? Although, it still doesn't do great. 20% falsified references when asking about research in the US isn't that great either, but still the difference is marked. So after that, I even had a conversation with Bukosi about this. I was like, explain this to me. Why is this happening? And if you look in the literature on why large language models hallucinate, you get all sorts of different explanations. Insufficient or noisy training data, yeah, that kind of makes sense. Training rewards the training that they give the models kind of forces them to give an answer because they get more points when they give an answer because they're more likely to get the right answer than saying, I don't know. And then the inherent limitations of next token prediction. You sort of get, you've got this momentum, you said this whole sentence, well, you can't really go back and correct anything, right? So these are some of the explanations but none of them gave me any clarity as to why this particular phenomenon was happening. Okay, this is where I get to the scaling laws. It was in January this year. I think it was in December the paper came out. And it was the first time I learned about this, something called superposition, which is super interesting, actually. And the idea, and Devin, you should probably explain this to everyone instead of me, but the idea is when you're trying to encode more concepts than you have sort of parameters to encode them in, right? They must overlap, okay? So all these vectors overlap. And if they overlap a lot, well, then it gets noisy because this one's very close to this one. So you don't know which one really it is. Let's say, if you've got so a good analogy is you're in a very big room, right? And if I'm in a big room and I'm talking to someone next to me, I can hear them very clearly. But if we all bunch together and we're all talking at the same time, now it's very hard to have that conversation, right? So this then explains, is the reasoning for the explanation of the scaling laws. As you expand, now you have less overlap of these concepts. So that gives this idea of sort of in any model, you have sort of this noise floor. So at any point in time when its activation is coming through, all these firing different vectors creates a bit of noise. So that's the first concept. And you actually see, he showed a picture of the scaling law. I went back to the HalluLens, which is a benchmark on hallucinations. And actually, they didn't plot this out, but they just gave the data. It turns out they're perfect scaling laws, right? Which is not a surprise. If that mechanism holds, which I think it does. But like I said, that does not explain all the results. It doesn't explain why Ghana is so much worse than the United States and is worse than Nigeria. So we had a hypothesis, and I should have mentioned at the beginning, but I'm working with some other folks on this that, well, I won't mention them now, but one of them is a mathematician who's been very helpful, and we came up with this, but I'll explain that later. The theory was effectively that concepts that are more present in the training set get encoded more strongly and therefore have a stronger signal, right? And so if you want to recall a fact in this case, then the concept signal has to exceed that noise floor, right? So again, if you have really, really big model, the noise floor is very low, you can retrieve more facts. Smaller model, very weakly encoded facts, they're not going to rise above the noise floor, and what you just get is just noise. So this is what we then tested. And I used the source verify thing. I don't think I need to go into a lot of detail about this, but it was the same kind of test where we're asking it to give very specific, like in this case, it was 10 references for each specific concept. And we were more intentional about the concepts that we chose because we wanted them to, actually this fits a power law. There's a thing I had the pleasure to learn about Zipf's power law, which is represents sort of the nature of those people who study languages will understand that. You know, lots of very frequent terms, and then it long tails to very few terms, right? So the concepts that we chose fit that as well. And we did that on purpose because the hypothesis was, you know, things like energy and health and education will have strong encodings, and therefore, in theory, should show up more in the smaller models. And that is indeed what happened. So we ran it. Actually, I've run like 35 different models up until now. I think this is 14 of them, and these are only dense models. If anyone wants to explain to me why mixture of experts models behave a little bit differently, I would love to have that conversation. But this is what came out. It turns out the P is the number of parameters, so how big the model is. That explains upwards of 50%. And the S being the signal strength, that explains another 13%. So it isn't, so in essence, what I'm saying here is that the scaling law is not just the size of the model, but also the representativeness of the concepts that you train it on. And this is the same plot, but I added in some other models so you can kind of see, so like GPT-5, or I did Opus on there. And they actually don't do, which is very interesting to me, very much better than the Llama 405B, which is extraordinary. Like that model does extraordinarily well. I had no idea. So this is just to illustrate that at the top end of the scaling law, it's not just linear. It's sigmoids, right? It curves because, well, what you see is that the difference in the improvement from 405B to, I don't know, GPT-5 is very little, but the parameter size doubles, even triples. It's on there. All right. Two other things I want to say about this. Oh, okay. Actually, I'll skip that one. Two other things. One is at the top end, it flattens off, meaning, okay, even though you might get a lot bigger, you're not going to get a big improvement in performance. That's important to understand. And I think that's what we've seen in general in the development of all these large language models that are kind of converging. And I think probably why we don't see a lot of really, really big open source models, because you don't get a lot more bang for the buck if you go up another, if you double the size, right? Down at this end, a very interesting thing occurs, which is it becomes more like, do you know Mad Libs? Anyone know that? Anyway, it's like a template reproducer, right? So down here, I think it was one of these two. For example, of the 240 references that it came up with, it only came up with 64 unique author names, and 24 times it used the author Smith, which I noticed because that's my last name, but it is a very common name. All it was doing was reproducing the sort of like the highest frequency concepts as references. One of them even returned the same article 8 times with a different date. So it's not really following any strong signal. It's just taking in, it makes sense, right? Because as you move here, you're starting to enter into the noise. And as you go through the noise, you're now picking up more random stuff from activation close by. All right, 2 more things I want to say. One is just to emphasize the fact, the hypothesis that this is driven by the overlap of concepts, the superposition regime, is that you would expect a smooth transition. You would not expect, if it was this overlap and the noise floor, right? You would not expect it to be good reference, bad reference, right? There's going to be some gradation in the middle, and that's exactly what you see. So on the left there is Llama 8B, on the right is 405B, and this is effectively sort of number of errors where green is low, and you can see as it comes this way, meaning as it gets smaller, the types of errors and the frequency of errors increases, right? And it happens in a nice continuous smooth way, as you would predict under a superposition regime. Oh yeah. And this one is likewise. If you if you think the frequency argument, if you buy the frequency arguments, then you would make the prediction that the citations that smaller models come up with will be more frequently cited citations, right? That's exactly what you see. So this is the median citation count of recalled papers, and these are the small models up there, and those are the larger models right there. And this actually is also a power law. So it seems to me that those two theories hold. Okay. So now I will try to wrap up. So what it seems like we're finding is that factual recall accuracy is predictable, driven by the strong superposition regime. And that idea blew my mind. Perhaps people who are machine learning researchers, it's not so surprising for them. But when something like a hallucination, not on a one-to-one basis, but on, if you do 100, you can, okay, it's going to hallucinate 20% of the time. I think that's a very interesting fact that can also be a very useful fact. One of the implications and why I mentioned epistemic inequality in the beginning is because this is just another example, maybe even it's an empirical demonstration of how the data sets that you use encode this epistemic inequality. And even if you make the models a lot bigger, it's not the rising tide raises all boats or whatever that expression is. You're just expanding the coverage, right? You're going down that long tail, but it's not universal improvement. Trying to hopefully make it a little bit more useful for some in the group. And I added the RAG thing because of the talk that happened this morning. But it sort of in my head, one of the reasons why I started this was because I'm very interested in all the work on small language models and using those and training languages on them. But I thought, geez, this is terrible, right? Are they just going to all hallucinate all the time? Why would we even use them? So one of the pieces of good news that comes from this is that you need to think about the signal and the noise ratio, right? So if you want to have it factually recall certain things, you don't need it to be as common as the most commonly cited references, if we're using citations as the example. You just need to get it above that noise floor, right? So maybe that's not, you don't have to do 10 to the 3 times as many. Maybe it's just 10 to the 1 or something like that, but maybe it's a more manageable. But it's important then where you know where it sits, right, vis-a-vis the noise floor. You can imagine that any post-training gains will be quickest for concepts that are very close to the floor, right? Not the long tail, but those would pass the floor quickly. And one last comment on the RAG. I didn't show any of these results, and we've got a little bit, and I don't think I have enough to talk about it really, but any approaches that you take, like RAG or chain of thought or doing a really long prompt or having specific things in a prompt, all of that does 2 things, right? And this is what you always have to balance. It adds noise, right? And maybe it adds the right information to strengthen the signal that you're looking for. And you have to balance that off. In a second, in the RAG, what I found, so Sonar, the perplexity model that has RAG, I was sure it's based on Llama 70B, I think it was. I was sure it would do better. It did worse. It did worse than Llama, and I couldn't understand why. And then when you look at which ones it does well on and which ones it does worse on, it makes a lot of sense. It did better on the low frequency concepts, and it did worse on the high frequency concepts. So things the model already knew about, don't use RAG. But things that the model did not know anything about, well, it didn't have any strong signals, so whatever it brought in rose above that floor. And I will end it just in time. Thank you very much.
Okay, are there any questions, comments, inputs? I'm sorry, I'm gonna have to run to join a meeting.
So, thanks for the presentation. Very interesting work indeed. My question is about your experiment setup. Seems like you experimented on a lot of model. Can you give us sort of like a workshop or share on how you've actually set up your experiment yeah, so that we can maybe benefit, because I'm really interested in this work, and it's something that I've come across quite a lot. But just simple question: how actually do the model know that they don't know something? And in terms of getting those references, right? So they end up hallucinating. But what differentiates those models that know that this does exist and this thing doesn't definitely exist?
Yeah, I didn't really talk about that, but that was that tool that I created at the very beginning, which, and I mean, I'm happy to meet with you afterwards and I can explain how I set it all up. But that tool effectively does what a human would do, which is it goes out, it searches, it finds candidate references, it tries to compare them by different fields, right? At its core, that's what it's doing. And so that's how, and then it comes back with a determination. Now, actually, something just really quickly, because it's so it's a smooth transition. The whole middle, like if you as a human have ChatGPT make up 10 references, some true, some false, and then go and try to find them, it actually gets crazy because of the way the superposition works and the overlaps work. It will give you the right title, maybe switch a word, the year will be 1 year off, and all the authors will be right. You say, well, okay, I guess that's not hallucinated. That's pretty close, right? But then they'll be, well, the title is good, the venue, like it was published in the right journal, but the authors are wrong and the date's wrong. Well, I don't know. Okay, what do you call that? So it doesn't come back with like a score saying we think it's 60%, but rather it grades all of the different fields individually, and then it gives you a score based on that. But then you can go look and say, okay, here's where I think it falls. If that makes sense. Is there any more questions? No?
No, Mahmuda will take over.
Oh, sorry.
Thank you. Thank you so much. Round of applause. Okay, so up next we have Ms. Siani. We have a second panel. And Ms. Siani will be our moderator.